And it looks like projectile motion is like really hard and different than what you already know. But I'm here to tell you, I want you to erase that from your mind, and I want you to hear me when I tell you that the equations that we are going to use for projectile motion are the exact same equations that you already know. The only difference is that we have now an x direction, and now we also have a y direction. So we have two different dimensions to worry about. So if I take a baseball or football or a rock and I throw it at some angle to the ground, we all know that it's going to trace out this curved path, right? But that curved path can be broken down and thought of, and this is the core principle that we have to understand in this lesson. That curved path can be broken down into two separate motions, right? And the horizontal motion is one of the motions that comprises this path, so it's going horizontally, and at the same time as it's doing that, it's also moving purely vertical. So you can think of when you throw a rock at a curved path, you can think of it, the curved path is a result of two separate motions which are sort of added together. One is the horizontal motion, just going that way, and the other is the up and down motion like this. That is going to be the most powerful thing that we're going to learn in this, and you have to understand it before we go any farther. And it's very, very simple. And because of this, what we do is we apply the equations of motion we already know to both of these directions separately. So it's the same equations, but we have to do it sort of twice because now we have a vertical motion to deal with and also a horizontal motion. So let's stop talking and draw a few pictures. All right, so let's draw a little picture of what's going on here. And this is going to be familiar to everybody because we've all thrown rocks and things like this. So here we have the XY axis here. And if I throw a rock kind of like at an angle like this, we all know that it's going to go up and then it's going to reach some maximum and then it's going to come down. Now, I cannot draw it perfectly, all right? But this path is called a parabolic path. You can also think of it as being a parabola. So parabola, or parabolic. This word comes from algebra. When we study algebra, we study parabolas all the time, right? A y is equal to x squared. That's a parabola that goes like a smiley face. This is an upside down frowny face. We learn in algebra the equations of these things all have squares in them, and that makes them parabolic or parabola. And when you're in algebra, students ask all the time, why are we studying this? Who cares? Well, here is your answer. Because every time you throw something, the path it traces out in a gravitational field, which is what we're in, is a parabola, a parabolic path. So it's one of the reasons, but there's lots of other reasons we study parabolas, but we're going to be getting comfortable with it here as well. All right. Now, as we throw it, it's important to consider that we have to have some sort of initial velocity that it's being thrown at some angle here, so v naught. This is a vector, right? Remember, what I'm saying is right here when the motion starts, I launch it, and it's at some angle. I'm going to draw the angle in a future picture here. I guess I could do it right now. You could say there's some angle here, and at some initial velocity up like this. And it turns out that just knowing the angle and whatever meters per second I launch it at that angle is enough to totally predict what this path is going to do. It's enough to predict how high it will go, because we know it goes kind of up and down like this. It's going to reach some maximum height above the ground like this, right? And also it's going to go some many meters down before it hits the ground again. So when we say that we're going to solve projectile motion problems, we're going to be using this idea to solve problems related to motion in a gravitational field called a projectile motion. So we might want to know how high does the object go before it falls again. We might want to know how far away it gets from the starting point but when it hits the ground. We might want to know what's the hang time, how many seconds does it remain in the air. We want to know many other things. We can construct problems, but those are the basic kind of questions that we are going to be asking. Now, I want you to remember that as this object travels along this curved path, the acceleration of gravity is always acting down. We call that a sub y because it's an acceleration in the y direction, and it's equal to negative g. So we've talked about this in free fall motion before. G is 9.8 meters per second, and since gravity acts down, and we typically choose the positive y direction up, we say that gravity is negative because it's acting in the negative direction. So the acceleration is negative 9.8 meters per second squared. I may have said the incorrect units before, meters per second squared. But this acceleration of gravity, it's acting purely in the down direction. right? All along this motion. It doesn't act horizontally because gravity always goes down like this. Now here's the punchline I want you to remember as we do the rest of this lesson. Because gravity only acts down, but the motion as it moves has an up and down component to it and a horizontal component to the motion, both of which is what traces out the curved path, then that's why we break the motion apart. Because if we think about the motion, then the gravity part of it, the acceleration due to gravity, the force of gravity, is really only acting in the vertical direction. It only affects the vertical part of the motion. The gravity has no effect on the horizontal part of this motion. This is a vector, and you can consider it having a horizontal component going this way and a vertical component launching it in the upward direction. But because gravity is acting purely down, it only affects the part of the motion that's angled up. This gravity has no effect to the horizontal aspect of the motion. So that is a main difference, and that's why we break motion up into two kind of sets of equations. One equation deals with a horizontal motion, where there is no acceleration of gravity because it doesn't act in that direction. And the other set of equations all have g, the acceleration of gravity, because it's only the up and down part of the motion. And to illustrate that a little more clearly, this motion, which is a curved path, we can break it into the y direction of motion and the x direction of motion. So if you could put a pair of glasses on that only analyze the vertical motion, notice what's happening is if you ignore the horizontal, if you ignore that it goes this direction and you just look at the up and down, what happens? It travels up in the y direction till it reaches a maximum height, and then it turns around and it begins to come down until it hits the ground. So if you could only look at the pure y direction, the motion goes straight up in the air and then it turns straight back down around and goes like this, and we have the acceleration of gravity, which is negative g. The acceleration of gravity, as we launch it in the upward direction, is what slows it down. And then once it kind of starts to go down again, it accelerates it, and so it hits the ground, speeding up as it's going down like this. So the acceleration of gravity is only acting in the y direction. And this is what causes it to go up and then stop and then turn around and come down again. But in the x direction, the situation is actually a lot simpler, because in the x direction, you just have motion going in this direction with some initial velocity. V naught means initial velocity in the x direction, right? But there's no acceleration here. There's no acceleration here. Why? Because gravity only acts downward. It doesn't affect the horizontal motion. That's so critically important that it seems so obvious, but I want you to really take a second to internalize that. Any motion that is a curved path through space, I can break it up into a horizontal motion and a purely vertical motion. But the equations that we're going to talk about in a minute that are affecting the vertical part of the motion will have the acceleration of gravity in them because it's part of that motion and it's acting in that direction. But the equations that are acting horizontally, they won't even have gravity in them because gravity does not act in that direction. And that is why it's so beneficial to break equations up, because the horizontal motion is much, much simpler than the vertical motion, which has the acceleration of gravity. All right, so let's talk about this a little bit more. We'll do a famous experiment. You could do this yourself. But let's say that I have a little platform here, right? So many meters above the ground. I'm going to draw another copy of it right here, right? What do you think I'm going to do on this platform? Probably already know what I'm going to do. All right, but at the top of this platform is Jason. That's me, right? I'm not an artist, so I just have a little smiley face, a little stick figure smiley face like this. All right, and I'm holding two little balls right here, and I put them right next to each other. Let's say I can hold them right here, right? And I'm going to do the same thing here. It's me right here, and so on, and I have, two little balls right here. Now, what I'm going to do is I'm going to take one of the balls, the first one, and I'm just going to let it straight fall down. And the other ball, I'm going to kick it. And it's going to be purely horizontal motion like this. So I'm going to have some initial speed of this ball, which is, I'm going to launch it this way. And I'm going to have this one, which has no speed at all. I'm just going to let it drop and gravity is going to take over. What do you think is going to happen? Well, the ball that falls down is going to accelerate down due to gravity, and it's going to hit the ground. It's going to speed up because gravity's acting on it every second, making it go faster and faster, and it's going to hit the ground. Now, the ball that I launch sideways is going to also hit the ground, but it's going to have a curved path. So what's going to happen here is this ball is basically going to go straight down until it hits the ground right there, right? So we can say that this is like the ground or whatever down here. And this ball, as I launch it this direction, is actually going to go, and it looks like I ran out of room, you see. Ran out of room a little bit. But basically it's going to go curve down like this, and it's going to hit the ground right here. Now this is not an exact perfect picture of what's going to happen, but it's going to hit the ground. But they're both going to hit the ground. We know this. But what is special about this? Well, what's happening is when this ball is launched this way and this ball is dropped straight down, the two balls will hit the ground at the same time, right? You can do this. You can actually go and watch videos of this, or you could just do it yourself. Just literally get a ledge or some table, two little marbles, and then let one fall, and the other one you just roll it as fast as you can so they depart the table at the same time, and look very carefully at the ground. And you will see that even though one of the balls is curved and flying away from the table, if you were to watch it, what's going to happen is, if I could use my fingers for the balls, they're both going to trace out different paths, but they're both going to hit the ground like this at the same exact time. Now, the first time I saw this with my own eyes, it kind of blew me away, because you kind of think that when you launch it sideways, that somehow like delays it. That the launching sideways delays it hitting the ground, but it doesn't delay it hitting the ground. Why? Because what's happening is this ball has two parts of the motion. It has a horizontal motion going this way, which is taking it away from the table ledge, but gravity is acting all the time in the vertical direction. Gravity is acting all the time in the vertical direction. Gravity is acting all the time in the vertical direction. Gravity only acts vertically, so it doesn't matter how much you kick it sideways. That motion of the sideways motion is, and I will say this 3 times, completely independent of the motion of the vertical motion going down. The gravity acting on the thing going down, that motion is completely independent than the horizontal motion. There is no interaction between those two. You need to, in your mind, when you see curved motion like that, separate the vertical and the horizontal motion. So I said I'd say it 3 times. The vertical part of the motion is completely independent of the horizontal part of the motion. And the 3rd time, the vertical part of the motion is completely and totally independent than the vertical part of the motion. All that's happening is that if you drop it straight away like this, and if you kick it sideways, gravity is still pulling it down every second the exact amount. The only difference is in every one of those seconds that it's coming down, the sideways motion makes it go a little bit more horizontally. So the gravity is making it come down at so many meters per second of increasing speed every second, meters per second squared, 9.8 meters per second increasing velocity every single second. So every second it's coming down the same amount. The only difference with the kicked ball is in every one of these seconds, it just gains a little bit of horizontal motion. So it has to hit the ground at the same time because gravity is only acting vertically. Now I have to say this 10 times because I want you to internalize it, because you have to feel that in your bones whenever you solve these problems. The biggest problem is a student will look at the problem, see a curved motion, and just flip out because they don't know how to handle it. What you do is you break the motion into horizontal motion and vertical motion, and you treat them totally separately. That's how you handle every one of these problems. All right? So let's take a little bit more of a detailed look at what happens when you throw a ball. What we're going to do now is we're going to take this picture of this ball and this trajectory. We're going to do a little bit of additional analysis and try to figure out a little bit more detail what's happening. Now, this is going to be a sketch that's not going to be exact, all right? But we can still gain a lot of insight from that. So let's kind of do the same thing. We're going to blow that picture up again. So if I launch a ball at some angle, right, what's going to happen is it's going to go up to some maximum height, and then it's going to kind of come down like this. Now, that's not a perfect parabola, but it's supposed to be a perfect parabola. You're going to have to kind of like bear with me a little bit here. All right. So what's going to actually happen is when we launch it, it's going to have some velocity in some sideways direction or in some angle direction like this, right? And then this is like at this point in time. And then at this point in time, if you could like analyze the velocity of what was going on right here, it would look something like this. And then at the very tippy top, it would have only motion going horizontally like this. And then maybe a little bit later here, it will have motion that would be something probably like this. And then you could do something, we don't really need to do the last one over there, but we could do something like this. Like this. So what's going on is initially we launch it with some velocity. We call it V0, right? That's the initial velocity at some angled direction. So what I want to do is I want to look at the different components, the x and y components of the velocity along the path. I told you in the very beginning of physics that the most important thing I can teach you is that for every vector, which is lots of things, vector represents velocity like here, acceleration, forces are vectors. Anything that has a direction and a magnitude is a vector. Magnetic fields, electric fields, I can go on and on. Vectors are basically everywhere. Any vector can be broken up into its components, the x component acting along the x-axis and the y component acting along the y-axis. And you can think of this velocity, which is at some angle, as being composed of some horizontal speed and some vertical speed that together which traces out the oblique speed v naught like this. And to draw that a little more clearly, I think I'm going to use purple here. Basically, you can take this arrow and you can kind of like come down here like this and say, all right, so acting in this direction right here is going to be Vx, and acting up vertically is going to be Vy. So you see right now, at this moment in time, there's a very large vertical component acting straight up, and there's a smaller horizontal component acting over like this. And with the magic of editing, I changed the lengths of my arrows here to make my point a little bit easier. But if you look over here, if you look at the velocity right here, you can break this into components as well. Horizontal and then also the vertical component right here. And so this is Vx and this is Vy. Now right here, notice that there's only a Vx direction because the motion is now purely horizontal, and Vy at this point is actually equal to 0. There is no up and down motion at the top. Why? Because at the very top of the arc, it's not moving up anymore and it's not moving down. At the very tippy top, it's not moving up or down. So at the very tippy top, the velocity in the y direction is 0, but in the x direction, it's still moving, of course, horizontally, right? And then when we get over here, you can draw this guy as a down arrow and then an over arrow right here to equal this guy. This will be Vy here and this will be Vx. And you can do the exact same here like this. So we'll do kind of a horizontal. So Vx and then Vy. All right. Now, along the entire path, no matter if I'm here or here or here or here, what's happening is gravity is acting vertically down on the ball like this, only in this direction. It is not affecting the horizontal motion here in the x direction at all. It's not even impacted at all. Now, once you look at the components of the vectors, notice what's happening. The length in the x direction, which means the speed at which the ball is going this way, is this big. Over here, the velocity in the x direction is completely unchanged. It's the same length. And over here, it's the same length. And over here, it's the same length. And over here, it's the same length. That's why I had to change the length of my arrows because I drew them a little bit long a second ago. But you get the point. As the ball flies, the speed in the horizontal direction never changed. That means if you could put glasses on and somehow that would wipe out the vertical motion and you would only see the horizontal speed, it would be completely unchanged. It would just be like this. It would be like my finger moving at a very constant rate to the right because gravity is not affecting the horizontal motion at all. So if you launch it at some angle, it has some component in the horizontal direction, it's just going to coast in that direction forever and ever unless something stops it like wind or if it hits the ground or something like this, okay? So these arrows are all the same in the horizontal direction. So that's because gravity is no forces are acting in that direction. But let's take a look at the vertical direction here. This was the actual, velocity at some angle. The vertical velocity was very high initially, but in the next instant of time, the vertical velocity is still pointed up, but it's much smaller. And then after that, the vertical velocity is reduced all the way to 0. And then after that, after it turns around, the vertical velocity turns around and starts to point down, but it's small. And then here, the vertical velocity is pointed, I didn't put an arrow here, but it's pointed down because the arrow has to be pointed down to make the arrow go down like this. It's down but larger. So the vertical part of the speed is very large, then smaller, then 0, then turns around, small, pointed down, and then larger. Why is that? It's because gravity is acting downward. Remember, what is gravity? G. 9.8 meters per second squared, right? G is negative 9.8 meters per second squared. What does this mean? This is meters per second per second. This means when the ball drops after the first second, it gains 9.8 meters per second velocity down. After the next second, it gains another 9.8 meters per second. It's in picking up speed. After the third second, it gains another 9.8 meters per second, again, pointed down. So what's happening is when I launch the ball up, it initially has a very high speed vertically, but because gravity is basically trying to make it speed up in the down direction, it's slowing it down. It's subtracting 9.8 meters per second from its initial large velocity, and it makes it smaller. And eventually, it continues to subtract velocity in that direction until it gets to 0. That's the top of the arc. And then it's trying to, again, subtract 9.8 meters per second in the down direction, so it gets a little bigger. And then it subtracts another 9.8 meters per second of its velocity down. So velocity is very large up, then smaller, then 0, then bigger negative, then bigger, bigger negative, because gravity is constantly trying to make it speed up in the downward direction. But notice that from this picture, you can see that gravity, this G here, it's only affecting the vertical part of the motion. The horizontal component is not affected at all. That is the point of the picture. That's the only reason I drew the picture, for you to see that visually. So when you visualize a baseball being thrown, I want you to, instead of looking at its curved path, I want you to mentally break it into a horizontal part of the motion, little vector arrows, and a vertical part of the motion, and try to understand that those two things are totally unrelated. All right. Now, I want you to recall, I think I'm going to do this on the next board. I think I'm going to recall the equations of motion in one dimension, right? Now, depending on your book, they may be written slightly different ways, but the way I write them is like this. In one dimension, let's just say we're talking about motion along the x direction. We had v sub x is v sub naught, initial velocity in the x direction, plus the acceleration in the x direction times time. That was equation number 1. And then we also used x is equal to x naught, so the position at some time in the future is equal to wherever you start from, plus v naught t, plus 1/2 times a in the x direction, of course, t squared. That was the second equation. And then we also derived a third equation, vx squared is equal to the initial velocity in the x direction squared, plus 2 times a sub x and x minus x naught. X minus x naught is the however far the thing travels. So you could say delta x, how far the thing moves. Now, if you don't know what these are, if you've never seen them before, if they scare you, then just stop. Just go back to my lessons on one-dimensional motion. We did not one, but 2 lessons on these equations, and then we did a ton of problems using them. So what's going on here is this equation lets you know the speed in the future. If you know the speed when you start in the x direction and its acceleration and how long in the future you care about. This equation is telling you where you are located in the future if you know where you start from, and you know the initial velocity you start with, and you know the acceleration, how much you're speeding up, and you know how much farther in the future you care about t. Now this equation just doesn't have any time. What you do is you solve this equation for t, stick it in here for t, and you solve it and you get this guy. So this equation really comes from the first 2. And it's useful if you don't know how long things are happening, how much time in the future. If you just know the distance and the velocities, but you don't know the time, this is a very equation to have handy. Really, these are the 2 main equations of motion. This one comes from the first 2. So let me double check before I go on. Vx, v naught x plus axt. X is x naught plus v naught t plus 1/2 at squared. Vx squared is equal to v naught x plus 2ax, and then x minus x naught. All right, so these are the equations I want us to use. Now, in your textbook, what's going to happen is you're going to flip to projectile motion, and it may write these equations down, but then what they're going to do is they're going to start throwing a bunch of additional equations at you involving gravity. And a lot of students think that these are like new equations, and I have to memorize a bunch of new equations. I actually don't want you to memorize any other equations other than these. These you probably do need to remember. Any other equations you see in your book or whatever book you're using, they're just going to come from these equations. And I'm going to show you that in a second. But I don't want you to memorize any other equations but these. I'm going to put on the board, remember. Me. If I had a sheet of notes that I could write down for this lesson, all I would do would be write these equations, because everything can come from these equations. But let me show you how we handle it when we then when we go in the future and we handle situations involving gravity. So what you're going to do is you're going to look in your textbook, typically, and what you can do is you can see, let's take a look in the x direction, and let's take a look in the y direction. So now these are the equations of motion in only one dimension. Now let's consider projectile motion. We have an arced path, we have an x motion, and we have a y motion. What I'm telling you ahead of time is that these equations are the only ones that matter. All you have to do is apply them to the x direction and the y direction. But don't forget, in the x direction, there is no acceleration, right? I mean, of course you could be pushing on it, okay? You could accelerate in the x direction, but I'm saying for projectile motion, it's when you launch something and you're no longer pushing it. It's just acting under the force of gravity, right? So you're not pushing it anymore. There is no force in the x direction, so nothing is accelerating in the x direction. So if I was going to write down the equations of motion in the x direction, all I have to do is put the acceleration equal to 0. And I would say that the velocity in the x direction would be the initial velocity in the x direction. Initial velocity in the x direction plus 0 for acceleration, because there is no acceleration in the x direction, times time. Notice over here, there was no acceleration in the x direction. There was no increasing of speed in the x direction, so ax just goes to 0, and this is the equation you get. And all it tells you is that the velocity in the future in the x direction is equal to the initial velocity in the x direction. It never changes. And notice, it didn't change. Here is the same velocity in the x direction as time goes on. That's all this equation is telling you. Then you look at the second equation. You say, all right, I'm going to write this one down. All right, x is equal to x naught. So I'll put the initial position of wherever you are for x, and then v naught t, right, plus v naught in the x direction times t, and then plus 1/2 a t squared. But a, I'm going to say, is 0. So this term goes to 0. So there is no acceleration term. So what you've figured out, and you could put this as v naught x, I guess. Right? What you figured out is that you have these two equations which look like different equations, but they're not different equations because they just come from the ones we have when you put the acceleration in the x direction equals 0. This is what your book will have. They'll remind you of these equations, then they'll write these new equations, and students think they have to remember these equations. But I can't remember that many equations. You'll make a mistake, so just forget it. Stop trying to memorize those equations. Just remember, really, it's only 2 of them. These, most of the ones you use, sometimes you use this one. Remember these and just put in, okay, in the x direction, there is no acceleration, and you can write these down anytime you want. Now, let's go in the y direction. In the y direction, if I have a velocity in the y direction, remember I told you that these equations govern the x and the y. Now, this was written down in the x direction because that's how we learned it, but I'm telling you this equation applies to motion along the y direction. So the velocity in the, replace it with the y, is equal to the initial velocity in the y direction here, and you have plus at, but we know acceleration in the y direction is negative g, so this becomes a negative g t. So you have vy is equal to initial velocity in the y direction minus gt. Boom, it looks like you have a new equation, but you don't. It's the same equation you had, it's just you replaced the acceleration with negative g. And then finally, the position in the y direction is equal to its initial position in the y direction. Why not? And then we have plus v naught t. So we can have plus v naught y t, which is initial velocity in the y direction t. And then we have plus 1/2 at squared, but a is negative g, so this becomes negative 1/2 at squared. Negative 1/2 times g times t squared. So this, again, looks like a new equation, right? But it's not a new equation. This equation comes exactly from the one we had. We just applied it to the y direction, and we said the acceleration was negative g. So do not try to remember these equations. You're not going to see a teacher tell you this too much, but don't remember these. Don't remember them. Just don't. Because if you try to remember these equations and keep them straight with these equations, eventually you're just going to make a mistake. Everybody will at some point, okay? So now what we have to do is take a look a little more closely as to what a typical projectile motion problem will have. Notice that when we launch the thing, we launch it at some initial velocity, and I didn't write it on here, but there's some angle to the horizontal. Typically, the problem will be something like we launch a rock at an angle of 37 degrees to the ground, and then the velocity is like 55 meters per second. Tell me how high the rock reaches. Okay, so we need to somehow incorporate the angle of the launch into these guys here. So let's go to the next board, and I'm going to write down some more equations that, again, I don't want you to memorize. I'm just writing them down so you can see how your book will arrive at them. But I don't want you to write them down because all you need is the ones I wrote, the top 3 that I wrote on the previous board. All right, I mean that quite seriously. So let's say that you know over here, like here's xy, and you are launching, you know, some projectile or whatever at some angle, like this, and there's some angle involved, right? Now, anytime you have something launched at an angle, we're going to call this guy, we're going to call this initial velocity like this. And we're going to break this guy up into motion in the x direction and motion in the y direction. Now, in the x direction, it's v naught in the x direction, and then we have in the y direction, v naught in the y direction. So in order to get the angled motion at a certain velocity, all we do at its angle, we have some x component of the initial velocity and some y component acting up. The horizontal and the vertical give us the total. Another way of thinking about it is that the angled velocity here can be thought of as a horizontal motion and a vertical motion acting together at these different velocities. And you can see it's a right triangle right here because this is a 90-degree angle. So it's not that literally this is equal to this plus this algebraically. It's just that the angle, if you would look at the motion due only to the horizontal and then the motion due only to the vertical, then those two velocities together would be the exact same as some velocity here acting at this angle theta. That's what's happening right here. Now from trigonometry, one of the things I told you was very, very important, right? We know that this in the x direction, v naught in the x direction is equal to v naught times the cosine of theta. And we know that v naught in the y direction is equal to v naught times the sine of theta. If you don't know this, if this isn't something that you understand and you're comfortable with, then you need to go back to my lessons on trigonometry and on vectors in the beginning part of physics. I told you, that's why I did those lessons. It was going to come back over and over again. So you know that the cosine of an angle is equal to the adjacent side divided by the hypotenuse. So the cosine of this is adjacent over hypotenuse. So then the hypotenuse is going to be equal, or the adjacent side is going to be equal to this times the cosine of theta. In other words, adjacent side, or I should say cosine, is equal to adjacent divided by hypotenuse. So if you were to divide this over, the cosine would be the adjacent side here divided by the hypotenuse. But I'm writing it this way because I want you to realize that what you're trying to figure out is the horizontal part of this velocity is equal to whatever the total velocity is times cosine of theta, which is, I want you to think of cosine as like a chopping function that reduces or demagnifies or chops down the entire velocity, which is acting at an angle, and gives you only the horizontal portion of it. So this cosine, every time you see a cosine, I want you to think of it chopping it down to the x kind of portion of the motion. So it's the total velocity multiplied by a fraction, which gives us only the x part of the velocity. And the y part of the velocity is equal to the total velocity times some fraction called the sine, which gives us the vertical part of the motion. So when you take the sine of theta and you multiply by the total velocity, it's like giving the projection in the vertical direction. When you take the total velocity times the cosine, it's like giving you the projection to give you the horizontal part of the velocity. So what we're going to do is take these guys, I have v naught x and v naught y, and we're going to put them right into these equations, right? So what you can do, I think I'm just going to do it right below here. What you can do is you can say that in the x direction here, we have vx is equal to v naught x. But what I'm telling you is that if you launch this thing at an angle, the v naught x is going to be v naught times cosine of theta. It's the total velocity times the cosine, which chops it into the x direction. We just said v naught x was equal to v naught times cosine theta from this triangle. And all we did was take that and we put it in here, and now we have a new equation which looks totally different and scary, but actually it's the same thing as, it's just plugging in something we know from trigonometry, right? And then down here, we can say that x is equal to whatever x naught is, plus v naught x times t. And the way I want to write that is v naught cosine theta multiplied by time. All I did was, again, v naught x, we know it's v naught times cosine theta. Why? Because the x part of the velocity is the total velocity times the cosine, which chops it in that direction. And that is what goes into this equation. So now you have a new scary looking equation, but really it just comes from what we already know from up above. Now let's do the y direction here. Here we have v sub y is equal to v naught y. So we're going to substitute in v naught times the sine of theta, and then we have minus gt. All we did was we said we have a y component of the velocity, but if you're acting at some angle, the y component of the velocity is just the total velocity times the sine, which kind of gives you the vertical projection of that. So v naught times sine goes into this position right here, and the rest of the equation stays. And then we have y is equal to here y naught. Then we have plus v naught t. We have the same thing, v naught sine theta t. And then we have minus 1/2 gt squared, minus 1/2 gt squared. All we did was look at this equation, and we put the initial velocity in the y direction, substitute it for the v naught sine theta. Why again? Because the vertical part of the velocity is v naught sine theta. All right, let me double check myself. Vx is v naught cosine theta, x is x naught plus v naught cosine theta times time. Vy is v naught sine theta minus gt, and then y is y naught plus v naught sine theta t minus 1/2 gt squared. So I'm going to say the same thing. Don't remember these, and don't remember these. You might say, thanks for wasting my time telling me, equations that you don't want me to memorize. Well, let me just tell you, memorize them if you want to. I mean, great, yeah, do it, but you don't need to. If you follow the path I'm leading you on, you should remember what you need to remember, but don't remember any more than that, because believe me, we have enough to remember already. All you need to really remember is the equations of motion that we learned in one dimension. And here they are. Here's a velocity. Here's the position as a function of time. Velocity is a function of time. And then we have an equation that doesn't involve any time, because some problems we don't know the time at all, and this one is very useful. But this equation comes from the other two. Now, these equations were originally written in the x direction because we're only talking about one-dimensional motion, but we can apply the same exact equation to the vertical part of the motion. But now we know that vertically, anytime we see an a for the acceleration, we put just negative g in there because gravity acts down. But in the x direction, we don't have any acceleration at all, and so we put 0 in for here. So when you do that, you get equations for the x direction and equations for the y direction, which look like totally new equations. Your book will give them to you. They may even circle them. But the problem is it encourages students that, oh, all these new equations, this is like so hard. But actually, it's just taking the original two equations, there's really only two, and just in the x direction, horizontally, there is no acceleration. So you put 0 for a. And in the y direction, you put negative g for the acceleration because gravity's acting down. You get what look like new equations, but they're really not new. And then you say, okay, anytime we have a problem with an angle, when we have an angle here, we know that the x component of the initial velocity is going to be whatever the total velocity is times the cosine. The y component of the upward velocity is going to be this times the sine. We take those two things, we stick them straight into what we just got before, and we get yet new equations, which again look very complicated. If I looked at these and you told me to memorize them, I would be like, I don't understand. So I don't want you to memorize them, because instead I want you to know that when you see v naught times cosine theta, that's just the x component of the initial velocity. Because this times the cosine, that's what it is. Same thing here. And v naught times the sine is the y component of the initial velocity. Same thing here. So don't remember them. What I am going to do, what we're going to do together, right, is when we solve problems, we're just going to write the basic equations down. And whatever we are given, we're going to substitute in. If there's an angle, we're going to take care of the angle, and we're going to put it in here, with a cosine or a sine as needed. But we're not going to overcomplicate ourselves by trying to memorize things. In fact, some books, when they get to these equations here, they'll just say, most of the time you're starting at 0, 0 in the coordinate system, so the initial position usually is 0 in the x direction, and the initial y position is usually also 0. So you can simplify these equations even more by putting zeros in here, and then they don't look anything like what you have been taught in the past. But instead, I want you to know that they don't come from nowhere. This is where they come from. Use them if you want to, but I'm not going to use them. When we solve our problems, we're going to write the basic equations down. We're going to apply it to the x direction, apply it to the y direction using our mind. That's going to help us remember these equations. It's also going to help us understand what we're doing. Because if I just give you these equations and say use them, then nobody knows what they're doing. And I don't want you to solve problems in that way. So watch this lesson a few times until you understand what's going on. The biggest takeaway is that the y component of the motion and the x component of the motion are totally unrelated, even though we think they're related because we throw things and we see them kind of behaving together, but they act separately. The equations are totally separated from one another, and that's how we're going to solve every problem. Follow me on to the next lesson. We're going to solve our first problem right now. Learn anything at mathandscience.com.